The topic for today's session is Introduction to Hypothesis Testing. Hypothesis testing is a fundamental concept in statistics that allows us to make inferences or educated decisions about a population based on sample data. As illustrated humorously in the slide, where a child wonders, "Am I shorter than the other kids?" Hypothesis testing helps answer such questions objectively using data and statistical reasoning. This method is essential in scientific research, engineering, social sciences, and business analytics, where assumptions or claims must be tested against observed evidence. Whether we're evaluating the effectiveness of a new drug, checking the durability of materials, or comparing product performance, hypothesis testing offers a structured way to validate or refute such claims with a defined level of confidence. In this lecture, we will explore the logic behind hypothesis testing, understand the types of errors, learn how to set up null and alternative hypotheses, and apply various statistical tests to real-world problems. Key elements of hypothesis testing. Null hypothesis, H0. This is the default assumption or claim that there is no effect or no difference. For example, there is no difference in the average height of this child compared to others. Alternative hypothesis, H1 or HA. This represents what we want to test or prove. It suggests a difference or effect exists. For example, this child is shorter than the average. One-tailed versus two-tailed tests. A one-tailed test checks for deviation in only one direction, for example, shorter than average. A two-tailed test checks for deviation in both directions, for example, not equal to the average. P-value. This is the probability of observing the data, or something more extreme, if the null hypothesis is true. A small p-value, typically less than 0.05, indicates strong evidence against the null hypothesis. Examples. Real-life applications include testing whether a new drug performs better than the existing one, whether a material has changed properties under stress, or whether machine components differ from specification limits. Understanding a hypothesis. A hypothesis in statistics is essentially a claim or belief about a population parameter, a quantity that characterizes some aspect of a population. This parameter could be the mean, proportion, standard deviation, correlation coefficient, and so on. The example shown here illustrates this clearly. I believe the mean weight of cereal packages is 300 grams. This is a hypothesis about the population mean, and it can be tested statistically using sample data. If the data supports this belief within an acceptable margin of error, we may retain the hypothesis. Otherwise, we might reject it in favor of an alternative explanation. Hypothesis testing provides a systematic and quantitative method to make such decisions rather than relying purely on assumption or intuition. The slide presents key concepts regarding hypotheses in research. Here's a summary of the main points. Null hypothesis. This represents a prevailing opinion or established theory in research. It serves as a starting point that assumes no effect or difference. Alternative hypothesis. This is a rival opinion that suggests there is an effect or difference. Evidence against null hypothesis. The null hypothesis remains accepted until there is sufficient evidence to reject it in favor of the alternative hypothesis. Sample evidence. A strong enough sample can provide the necessary evidence needed to disprove the null hypothesis, leading to the acceptance of the alternative hypothesis. The slide provides several examples of null and alternative hypotheses, H0 and H1. Here's a breakdown of each example. Height of males, H0. The mean height of males equals 174 centimeters. H1. The mean height of males is greater than 174 centimeters. Support for nuclear power, H0. Half of the population supports the nuclear power plant. H1. More than half of the population supports the nuclear power plant. Overtime work equality, H0. The amount of overtime work is equal for males and females. H1. The amount of overtime work is not equal for males and females. Interest rate and gold price, H0. There is no correlation between the interest rate and gold price. H1. There is a correlation between the interest rate and the gold price. These examples illustrate how hypotheses are structured in research, focusing on establishing a relationship or difference based on statistical evidence. Two-tailed test. The slide explains the concept of a two-tailed test in hypothesis testing. Here's a summary of the key points. A two-tailed test is appropriate when there is no specific reason to expect a deviation from the null hypothesis in only one direction. Deviations from the null hypothesis are considered interesting in both directions, either above or below the hypothesized value. The alternative hypothesis in a two-tailed test typically takes the form of different from, indicating that it could be either greater than or less than the null hypothesis value. One-tailed test. The slide outlines the concept of a one-tailed test in hypothesis testing. Here's a summary of the key points. A one-tailed test is used when it is known beforehand that only deviations in one direction, either positive or negative, from the null hypothesis are of interest. The test evaluates whether the observed value is significantly greater than or less than the null hypothesis value, but not both. The alternative hypothesis in a one-tailed test typically takes the form of less than or greater than, specifying the direction of the expected effect. The slide, titled Logic Behind Hypothesis Testing, explains how hypothesis testing works using a population and a random sample. It presents a population with a mean age of 50, null hypothesis, and a random sample with a mean age of 45. The common assumption is that the mean age is 50, but the sample suggests otherwise, leading to the rejection of the null hypothesis, subject to appropriate statistical tests, which we will see shortly. The illustration features two characters, one representing the population and the other the sample, with speech bubbles clarifying the hypothesis testing process. The slide, titled Risk of Being Wrong, explores the uncertainty in hypothesis testing by comparing it to the legal principle, not guilty until proved otherwise. It explains that just as an innocent person may be mistakenly proven guilty, the null hypothesis can be rejected despite being true. The slide highlights that this risk stems from sampling error in statistical analysis. The slide, titled Significance Level, explains the concept of significance level in hypothesis testing. It covers 4 key points. When the null hypothesis is rejected, there is always a risk of making a wrong conclusion. This risk, called the p-value or observed significance level, can be calculated. The researcher determines the maximum risk they are willing to accept, known as the significance level. A commonly used significance level is 5%. The slide, titled P-value, visually explains the concept of p-values in hypothesis testing using a normal distribution graph. It highlights two-tailed rejection areas, where extreme values lead to rejecting the null hypothesis. The graph illustrates different p-values calculated using the normal distribution formula, Excel equation, with key annotations marking their significance. P-value for any particular value of z, say 2.5, as shown in the figure, is the cumulative probability towards the right from the line shown, calculated at 1 minus the cumulative probability up to z equals 2.5 from minus infinity. P-value for any particular value of z, say 1.5, as shown in the figure, is the cumulative probability towards the right from the line shown, calculated as 1 minus the cumulative probability up to z equals 1.5 from minus infinity. The extreme value within the acceptable region is 1 minus cumulative probability up to z equals 1.96, corresponding to a 95% confidence interval, two-tailed, p equals 0.025. On the left tail, the extreme value of p is the cumulative probability up to minus 1.96, corresponding to a 95% confidence interval, two-tailed, p equals 0.025. This slide helps to understand how p-values determine whether the observed data is statistically significant. The slide outlines the steps involved in hypothesis testing, a fundamental concept in statistics. It provides a clear and concise guide to the process, breaking it down into 3 essential steps. Set the hypotheses. Establish the null hypothesis, a statement of no effect or difference, and the alternative hypothesis, a statement indicating an effect or difference. Calculate the p-value. This measures the probability of obtaining the observed results under the assumption that the null hypothesis is true. Decision rule. If the p-value is less than 5%, reject the null hypothesis. Otherwise, the null hypothesis remains valid. Regardless of the decision, the p-value must be provided as justification. Testing mean, null hypothesis. Mean equals x0. Alternative hypothesis, two-tailed. Mean is different from x0. Alternative hypothesis, one-tailed. Mean is less than x0. Alternative hypothesis, one-tailed. Mean is bigger than x0. Testing mean, alpha known. Calculation of p-value. Step 1. Calculate the standardized sample mean. The formula for calculating the z-score is z equals sample mean minus population mean divided by population standard deviation divided by the square root of the sample size. Step 2. Calculate the p-value. The p-value tells us how likely it is to get this kind of result under the assumption that the null hypothesis is true. Step 3. Compute the p-value in Excel. To calculate the p-value in Excel, use the following formula. P-value equals 1 minus norm.s.dist, z, 1. Testing mean, alpha unknown. Calculation of p-value. Step 1. Calculate the standardized sample mean. The formula for calculating the t-score is t equals sample mean minus population mean divided by sample standard deviation divided by the square root of the sample size. Step 2. Calculate the p-value. The p-value tells us how likely it is to get this kind of result under the assumption that the null hypothesis is true. Step 3. Compute the p-value in Excel. To calculate the p-value in Excel, use the following formula. P-value equals t.dist.2t, x, degrees of freedom. In this case, degrees of freedom equals n1, and 2t defines a two-tailed test. Suppose a manufacturer claims that the average lifespan of their light bulbs is 1,200 hours. You want to test whether the actual average lifespan is different from this claim. You gather a random sample of 30 light bulbs and find that the average lifespan is 1150 hours with a standard deviation of 100 hours. Hypotheses. Null hypothesis, H0. The average lifespan of the light bulbs is 1200 hours H0. Mu equals 1200. Alternative hypothesis, HA. The average lifespan of the light bulbs is not equal to 1200 hours, two-tailed, HA. Mu does not equal 1200. Solution. Significance level. Choose a significance level, alpha. Common choices are 0.05 or 0.01. For this example, we will use alpha equals 0.05. Test statistic. Since the sample size is 30, which is equal to or larger than 30, we use the z-test for the sample mean. Formula for the z-score. The formula to calculate the test statistic, z-score, is z equals sample mean minus population mean divided by population standard deviation divided by the square root of the sample size, where sample mean equals 1,150 hours, population mean equals 1,200 hours, sample standard deviation equals 100, sample size equals 30. Compute the z-score using the given values. Z equals 1150 minus 1200 divided by 100 divided by the square root of 30. This simplifies to z equals minus 2.74. Critical value. For a two-tailed test with alpha equal to 0.05, the critical z-values correspond to the 0.025 and 0.975 percentiles of the standard normal distribution. Using z-tables or a normal distribution calculator, we find critical z-values negative 1.96 and positive 1.96. Conclusion. Calculated test statistic. Z is approximately negative 2.74. Since negative 2.74 is less than negative 1.96, we reject the null hypothesis. The p-value calculated using the Excel equation is 0.003, which is much less than the alpha value. Hence, the p-value justifies the rejection of the null hypothesis. Example 2. Imagine a group of researchers wants to determine if a new teaching method affects the test scores of students. They compare the scores of students who were taught using the new method against the traditional method. Average test score equals 70. A random sample of 15 students who were taught using the new method yielded an average test score of 75 with a standard deviation of 10. Hypotheses. Null hypothesis, H0. The mean test score of students using the new teaching method is equal to the mean test score of those using the traditional method. H0. Mu equals 70. Alternative hypothesis HA. The mean test score of students using the new teaching method is not equal to the mean test score of those using the traditional method, two-tailed. HA. Mu not equals 70. Significance level. Choose a significance level alpha. Common choices are 0.05 or 0.01. For this example, we will use alpha equal to 0.05. Test statistic. Since the sample size is n equals 15, which is less than 30, we can use the t-test for the sample mean. The test statistic is calculated using the formula t equals x bar minus mu, divided by s over square root of n, where x bar, the sample mean, equals 75, mu, the population mean, equals 70, s, the sample standard deviation for n less than 30, equals 10, n, the sample size, equals 30. Substituting the values in, we get t equals 75 minus 70, divided by 10 over square root of 15, which equals 1.94. Critical value. For a two-tailed test with alpha equals 0.05, df equals n minus 1 equals 14, the critical t-values correspond to the 0.025 and 0.975 percentiles of the standard normal distribution. Using t-tables or a student t-distribution calculator, we find critical z-values minus 2.145 and 2.145. Conclusion. Calculated test statistic. T approximately equals 1.94, since 1.94 is between minus 2.145 and 2.145, we fail to reject the null hypothesis. P-value equals 0.073, which is greater than the alpha by 2 value, and hence, the null hypothesis is rejected. Example 3. A nutritionist wants to determine if a new dietary supplement increases body weight gain compared to a standard diet. The standard diet results in an average weight gain of 5 kilograms after a month. A sample of 20 individuals taking the supplement shows an average weight gain of 6 kilograms with a standard deviation of 1.5 kilogram. Hypotheses. Null hypothesis. H_0. The mean weight gain with the supplement is equal to the standard diet, 5 kilogram. H_0. Mu equals 5. Alternative hypothesis. H_A. The mean weight gain with the supplement is greater than the standard diet. H_A. Mu greater than 5. Significance level. Choose a significance level, alpha. Common choices are 0.05 or 0.01. For this example, we will use alpha equals 0.05. Test statistic. Since the sample size is n equals 20, n less than 30, we can use the t-test for the sample mean. The test statistic is calculated using the formula. The t-statistic is calculated as follows. T equals the sample mean minus the population mean divided by the sample standard deviation divided by the square root of the sample size, where x bar equals sample mean equals 6, mu equals population mean equals 5, s equals sample standard deviation, n less than 30, equals 1.5, n equals sample size equals 20. Substituting the values in, we get the t-statistic is calculated as follows. T equals 6 minus 5, divided by 1.5 divided by the square root of 20, which equals 2.98. Critical value. For a one-tailed test with alpha equals 0.05, df equals n-1 equals 19, the critical t-value corresponds to the significance level 0.95, 1 alpha, equals 95%. Using t-tables or a student t-distribution calculator, we find the critical t-value as 1.729. Conclusion. Calculated test statistic. T is approximately equal to 2.98. Since the calculated t-value, t equals 2.98, is greater than the critical value, t equals 1.729, we reject the null hypothesis. P-value for t equals 2.98, and the degrees of freedom df equals 19, equals 0.003847. Since p is less than alpha, equals 0.05, the alternative hypothesis is accepted.